This is the lecturette for section 15.4, the last section in our introduction to equilibrium, and it involves Le Chatelier's principle, which has to do with what happens when an equilibrium exists and is just disturbed in some way. How does the equilibrium respond? And so we're going to start out by talking about Le Chatelier's principle, which is the principle that governs this. And then we'll look at three of the principal kinds of changes that happen to equilibria that cause them to go out of equilibrium, and then what happens when they go back in. So we'll be looking at what happens if a reactant or a product is added or removed from the system. We'll look at what happens to a change in volume of the system. That mainly has impact on gas phase equilibria. And we'll look at changes in the temperature and how temperature changes affect equilibria. So let's start out by looking at Le Chatelier's principle. Le Chatelier's principle basically says that if a system's at equilibrium and it's disturbed, what happens is that the system will want to get back to equilibrium, and it's going to do that by reacting in the direction that minimizes that disturbance, that kind of offsets the disturbance. So if the equilibrium is pushed on in some way, it's going to respond by going back in the other direction from where it was pushed. So we're going to start by looking at a water tank analogy. We have two water tanks connected by a pipe, and the two levels of water are the same. It's not same amount of water in there, but same level of water in both tanks. If we add water to the second tank, that is, we add water into here, that's our perturbation. That's perturbing our equilibrium. So now we're not at equilibrium anymore, and the system's going to respond by, not surprisingly, having water flow this way until equilibrium is reestablished there. And so that's the response to this of the system. So we added water here, and the system responded by removing water from there. So the system responded by minimizing the perturbation. And so for our system, we started at equilibrium over here. This is at equilibrium. After we perturbed the system, it's not at equilibrium anymore. And then the system responds to go back to equilibrium. It's at equilibrium both here and here, but it's a new equilibrium. It's not the same equilibrium state, this one and this one, but they're both at equilibrium. So now let's look at chemical systems for the rest of this time. We're going to start by doing just conceptually what happens if we have a chemical system and it's perturbed. Let's say we have our iron thiocyanate equilibrium, and let's say it's at equilibrium, and what happens is, at equilibrium, the ratio of the products over the product of the reactants is equal to the rate constant K, which at 25 degrees is 142. Notice what we're going to do is we're going to add some iron into here. Let's assume we add some extra, it's at equilibrium, we're going to dump in some extra iron, 3+. That doesn't affect K. K stays the same. So because we're not changing the temperature, the K is constant. And what that means is that now we have too much iron 3+ for being at equilibrium. So our Q value is going to be less than K. That is our reaction quotient value. If we increase this, the value of this fraction, which is the reaction quotient Q, is going to be less than K. So we're not at equilibrium. And because we're not at equilibrium, it wants to go back to equilibrium. Because we have too much of our reactant, because we added some on, the equilibrium will shift in that direction. And so the perturbation is adding this. The result is reacting this to make more product. And then what will happen is as this reacts, these concentrations will decrease, that concentration will increase until it goes back and reaches the equilibrium constant K. Let's take this imaginary equilibrium system. A plus B go to make C plus D, and the equilibrium constant is 4. We've just kind of made that up. And so we're going to start with 0.8 molar A, 0.6 molar B, 0.05 molar C, and no D. And we're going to equilibrate, allow those to go to equilibrium. And so they start out with what they are in their color code. You can see what they are. And it comes to equilibrium, you can see the concentrations have stopped. And so we had our initial concentrations. Here are equilibrium concentrations. If we were to plug these concentrations into the equilibrium expression, we would get 4. But now let's disturb the equilibrium. Let's, for example, add some extra C. So this is the line for C. So we're going to add some extra product. So if we add some extra product, what happens is this line here is moved up. So we've just increased our amount of C by a bunch. And so our equilibrium value was 0.95, and now it's 0.671. So we've added about an extra 40-50% of product C. And what we expect if we add C is that the equilibrium should shift in a way to offset that. So we expect it should go back to the left. So let's re-equilibrate and see what happens. So when it re-equilibrates, C and D decrease. So which means that C reacts because it wants to get rid of C because you added some. But when C reacts, D also has to react. So both of these go down in concentration. And at the same time, we're forming more A and B. So A, which is B, which is this line, and A, which is this line, are increasing. Okay, so let's start that again. Let's come to equilibrium. And instead now, let's add some B. So we're going to increase some B. So we increase some B. This line here has gone from here to here. So we're at equilibrium. We've added extra B. And what we expect is the reaction will shift to the right. So let's equilibrate and see what happens then. And in fact, it does. So we see that A and B decrease in concentration because we added B. So A and B are going to decrease, make more C and D. So we see the C and D increasing in concentration. Let's do one more of these. Let's come to equilibrium. Oh, let's reset. Let's come to equilibrium first. And now, instead of adding B, let's remove B. Let's make B go away. Not all the way to 0. Yeah, let's go to 0. So we've removed all of our B. So we've decreased the amount of B, and so to offset that, you need to make more B. So we should see C and D reacting backwards to make A and B. So let's re-equilibrate and see what happens. And in fact, it does. So because we removed B, C and D react to make B and A. So C and D decrease in concentration. That's these two. And A and B increase in concentration. That's those two. So that's kind of a graphical concentration time kind of view of Le Chatelier's principle for concentration changes. And now let's look at a numerical example. What we want to do is look at that same system we were looking at earlier, the iron thiocyanate system. The equilibrium constant is 142. And we have a system that's at equilibrium, where the concentration of iron thiocyanate is 0.0768, and both the iron 3 plus and the thiocyanate are 0.0232. So that's at equilibrium. And then what we do is we add some extra iron 3 plus. So we've added extra iron 3 plus, so now the iron 3 plus concentration is 0.0300. So it's no longer at equilibrium. So the first question is, in which direction will it shift to reattain equilibrium? And because we added iron 3 plus, it's going to shift to the right. So we're going to lose iron 3 plus and thiocyanate, and we're going to gain iron thiocyanate when it comes back to equilibrium. So now let's look at this numerically, and let's go review our pathway for determining equilibrium concentrations. And what you do is you write the equilibrium expression first. We have that. You construct an ice table, which we'll do in a second. You express the equilibrium concentrations in the ice table in terms of the initial concentrations and how much you expect to react. So the key is we don't know how much is going to react when we reattain equilibrium. And let me go back for a second to here. Essentially what we're looking for is when it comes back to equilibrium, it goes from, say, here to go back. And that's what we're looking for. How big is that change when you don't know it graphically? So we're looking for that change. Then we're going to insert these terms based on initial concentrations and the amount reacting into the equilibrium expression and use the equilibrium constant K to determine the value of X. And for the most part, you'll find this the hardest step because sometimes it involves a fair amount of algebra and using the quadratic equation. And then once we have X, then it's easy. We use X in the initial concentrations to determine the equilibrium concentrations. So let's see how this works. So we know that the reaction is going to be shifting to the right because we added extra iron. And so therefore, iron and thiocyanate are going to react. So they're going to change by minus X. X is defined by how much change is going to occur. The amount of iron thiocyanate then that gets made is plus X. And that's because one of these reacts with one of these to make one of these. If there was a 2 here, this would be plus 2X over here. So then our equilibrium concentrations are 0.0300 minus X, 0.0232 minus X, and 0.0768 plus X. And so that's our equilibrium concentrations in terms of our initial concentrations and X, the amount reacting. And so the next step is to determine what X is. And we do that by inserting these values, these terms here, into the equilibrium expression. So we know that at equilibrium, these will give you 142 when inserted in. So we put in our products, our reactants, and you then have an equation that has only one variable, x, and from then, it's algebra. And so you need to rearrange this equation into the form of a quadratic equation, where it's 0 equals AB. Essentially, it's the ABC version of ax squared plus bx plus c. And so there, for the quadratic equation, a is 142, b is minus 8.55, and c is plus 0.220. You insert those values into the quadratic equation, and you get two values out again when you're done. And when you do, one of those values doesn't make sense. So remember that the amount of x, the amount of iron left, is going to be 0.03 minus x. If this was x, you'd end up with a negative amount of iron 3 plus, and that's not possible. So this is not a possible answer, so this is the answer you get. You use x now and these terms to determine the amounts at equilibrium. And so what happens is the iron 3 plus is going to be 0.0300 minus x, so that's that amount. The iron thiocyanate is 0.0232 minus x, so that's that amount, just subtracting, because we know what x is, because x is equal to 0.00267. So that's what we're using for right there, and for all of these. And then when you add that value to the amount of iron thiocyanate there originally, you come up with that. So these are our equilibrium concentrations, which is what we were looking for. Okay, now let's turn to changing the volume of a equilibrium system. And this is only important for gas phase equilibria. And the general idea is, from a conceptual point of view, makes sense, that smaller volume, decreased volume, favors fewer moles of gas. And so what happens is, if we have an equilibrium where we have, say, 2 moles of NO2 gas phase reacting to make 1 mole of N2O4 gas phase, the N2O4 will be favored at small volume, and the two NO2s, which take up twice as much room in terms of moles, will be favored at large volume. And so if you decrease the volume, the equilibrium will shift to the side that has fewer moles of gas. Notice, just like in the case of changing the concentrations of things, there's no change in K. K does not change. Increasing the volume will shift the equilibrium to the side that has more moles of gas. So in our equilibrium here, I'll rewrite it here because it's a little crowded over there. If you increase if you have a system like this system and it's at equilibrium, if you increase the volume, the equilibrium would shift to the left. If you decrease the volume, the equilibrium will shift to the right. So decreasing volume will go to the side that has fewer moles. Increasing volume will go to the side that has more moles. If your gas phase equilibrium has the same number of moles on either side, there is no volume effect. So now let's look at a numerical example of this. What we have is we have a system involving this equilibrium where it's at equilibrium and the NO2 concentration is 0.314 molar and the N2O4 concentration is 0.143 molar. And the change we make is we go from a 2-liter container, we compress it into a 1-liter container. So we're decreasing the volume. Because of that, we want to favor the side that has fewer moles of gas, so we're going to shift to the left. So it shifts to the left. So we know which direction it's going to go into, and now our goal is to find out what will the concentrations be once it reaches equilibrium. And to do that, we're going to build a nice table. The first thing to think about, though, is that we had these concentrations and we halved the volume. So the volume went from 2 liters to 1 liters. So the new NO2 concentration is going to be twice what it was to begin with, because this was that many moles per 1 liter. Now it's that many moles. It was that many moles, but it was in 2 liters. That many moles per liter in 2 liters, and now we've decreased it to 1 liter. So that becomes twice, so it's 0.628 molar. And likewise, the N2O4 was in 2 liters, and now it's been compressed into 1 liter, so the N2O4 concentration, nu, is going to be twice what it was, 0.286 molar. And so then those are our initial concentrations that we have to deal with. Those are the concentrations we're starting with when this system is going to now try to go back to equilibrium. And we know that it's going to go to the left based on the Chatelier's principle because we compressed it and wants to favor the side with fewer moles of gas. So we're going to make X moles of this. And different from last time, 2 moles of NO2 are going to react for every 1 mole of this. So this is going to be minus 2X. So at equilibrium we have 0.286 plus X and 0.628 minus 2X. So those are our equilibrium concentrations in terms of the initial concentrations in X. Next is we insert those into the equilibrium expression. So this is the equilibrium expression. It's the products squared, because of that, over the reactants. And we just put in our values. So this goes there. This goes here. And that has to equal the equilibrium constant K. And so then again, it's a quadratic equation. So you rearrange this, make your quadratic equation, solve for X, and you get 2 versions of X. Only one of them is reasonable because one of them is going to have to fit with 0.628 minus 2X. So that's not possible because it would give you a negative concentration of NO2. So we now know X is this, and we know our initial concentrations and our final concentrations in terms of X, and so we can find our final concentrations. So the NO2 is going to be 0.628 minus 2X, which is that, and we're using for X, using the X we found from the quadratic equation, 0.0672 molar. And the N2O4 concentration is going to be 0.286 plus X, and that comes out to that. Finally, if you want, you can check, it's not a bad idea, is to put these values back into the equilibrium expression, because we should have reattained equilibrium, and see if you get the same number, and in fact you do. So they do equal K when put into the reaction quotient. Our final perturbing effect we'll look at is a change in temperature on the equilibrium. And to think about this, what we have to do is we have to consider heat, either produced or absorbed during a reaction, as either being a product or reactant. In an exothermic reaction, you know that a reaction gives off thermal energy, gives off heat. So we can think of heat as being on the product side of the equation. For an endothermic reaction, thermal energy is absorbed by the reaction, by the system as it's happening. And so you can think of heat as being on the reactant side of the equation. So when temperature increases, it's like adding heat. It's conceptually like adding heat. And so if you were to add heat, the exothermic reaction would shift to the left. And therefore, you would make more products more reactants at the expense of products. If the temperature increases and it's an endothermic reaction, it's like you're adding heat to an endothermic reaction, so the reaction would shift to the right. And so you'd make more products at the expense of reactants. On the other hand, if you decrease the temperature, that's like removing heat. And so for an exothermic reaction, if you remove heat, it's going to drag the reaction that way, and you'll make more products. If you remove heat from an endothermic reaction, it's like removing a reactant, and so the system will shift to the left and make more reactants at the expense of products. And so this is tabulated in this handy table. Okay, so first let's think about it in terms of a qualitative idea, and then we'll look at a numerical treatment of this. First of all, we have our NO2, N2O4 equilibrium, and written with the NO2 as the reactant, N2O4 as the product. Delta H for that reaction is known to be minus 57.1 kilojoules per mole, so it's exothermic. So a handy thing to do is to rewrite the equation with heat on the side where you'd find it. And heat is it's an exothermic reaction, so heat is a product. Therefore, if temperature increases, it's like adding heat, so the reaction is going to shift to the left. And the key here is that in the case of temperature changes, K, the equilibrium constant K, changes. And in this case, you're going to have more reactants and fewer products. And therefore, K, because remember, K is products over reactants, so if you have fewer products and more reactants, K is going to decrease in this particular case. We can use an equation to estimate what K would be based on the K we know and the delta H, and that's using what's called the Van Hoff equation, which is the same person, but it's not related to the Van Hoff factor. And it's in the same form we've used in a couple of other things. We use the same mathematical form for vapor pressure as well as for the Arrhenius equation for rate laws, rate constants, and activation energies. And so here we have the natural log of the equilibrium constant at two different temperatures. It's equal to minus the delta H for the reaction times 1 over the second temperature in Kelvin minus 1 over the first temperature in Kelvin. And the way this works is basically like we've done in other cases. There's 5 variables, K1, K2, T1, T2, and delta H. And essentially you just plug in 4 of those and find the fifth. Normally what you would do is you would use it to predict the equilibrium constant at a second temperature. So in our reaction here, we have an equilibrium constant of 0.635 at 1150 Kelvin. And we're asking what will happen to the O2 concentration when the temperature is increased. Well, the O2 is a reactant. The system is exothermic. So it's exothermic, so there's heat on the product side. And therefore, if the temperature is increased, the reaction is going to shift that way. So the O2 concentration will increase. The second thing you can do is you can estimate the value of the equilibrium constant at that temperature. We know the equilibrium constant at 1150. What's the equilibrium constant going to be at 1260? We know delta H, we know T1, we know K1, so all we have to do, and we know T2, so all we have to do is figure out K2. So you essentially set up the equation, plug in all the variables that you have, and solve for K2 numerically. And so you get your K2 there, and not surprisingly, it is at that higher temperature a smaller value.